Hey there, I'm Teacher Jess and welcome back to Geo Cafe. How are you? Hope you guys have had a decent week so far. Got coffee ready. It's a new mug this time. Someone bought me a lovely mug. Coffee makes the world go round. I thought that was perfect for Geo Cafe. A lovely little geography and coffee pun. I'll take it. Geography teachers, we love bad puns. What I wanted to mention before we actually start today's video was I know that there are many students that are busy prepping for exams or I don't know, test series or whatever else is coming up now. Um, if there is anything that you would like me to revise before or to like help you with your revision before you go into your exams, you can let me know. So maybe send a message in the chat or I don't know, leave a comment depending on where you're watching this. Um, Let me know if there's something you want me to recap, something that you're maybe struggling with. If it's small little topics or several topics, I can maybe do one video covering all the different questions, depending on how in depth I need to go. If it's a map work question, then I would probably have to do a separate video. I find that the way that I cover map work is you have to show with some examples and calculations, and I can't seem to do that in the live streams because I can't share the screen and do the actual sketches and calculations. Everything just bugs out. So I will do a pre-recording and then put that up onto YouTube. But yes, if there is anything that you would like me to go over, if you've got exams coming up, something that you're not happy with, something that you need a refresher on, and let me know, and I'll happily include that in a video. Okay. So today's video is a little bit of a combination of map work and atmospheric science. It's one of those sections that gets repeated every year from grade 10. And every year you build on it a little bit more as you learn a little bit more about atmospheric science. So what we're going to be looking at is synoptic weather maps and some weather station models. So it's just understanding how to read them, what they're actually telling us. It's quite different to normal maps that you would read for like navigation or land use or anything like that. It's what we can interpret about the climate, about the season, about the small scale weather events. Yeah, so we'll go into all of those elements. Okay. Now, oh no, there it is. Remember, so where's my map? So this is just an example of what a synoptic weather map looks like. I get all of my maps from the South African weather services. Oh, let me just find that. Let me just show you the website. Yes, service. The South African Weather Service. I'll let that load and we can just look at the map in the meantime. Here we go. So this is what a synoptic weather map looks like. So you can see, obviously I'm going to use South Africa for all of my examples because that's where I'm based and that's what my curriculum is on. So here we can see South Africa. You can see the outline there. Hope you can see it a little bit more. Zoom in. Oh, am I just blind? Hello, welcome to the group. Okay, well, that doesn't actually matter. Okay, so we have the outline of Southern Africa over here, and here is South Africa. You'll see that it's littered with these lines. I will also go into what those lines are, but those are isobars. So they show us what the pressure is in the atmosphere. Then these little symbols all over South Africa, those are weather station models, and I'll show you how to read. Okay, a few things to note. You can, on the side over here, you can see what time this was taken. You'll always notice it's at 2 in the afternoon. It's for sake of consistency. So if we're looking at weather, synoptic weather maps of different days, it's always at the same time of the day. And you will notice the date over there. So this is 2019, the 6th of February. See if this website's working. Yes. So I think it's here by observations. Yes, synoptic charts. This is a different version. This is the same thing. The lines show you pressure. These are your cold fronts and warm fronts. But I want to find what are the historical ones. And we're going to randomly download. So you can see they name it according to the date. So that's the year, the month, and the day. Oh no, it still has that style. And there's nothing wrong with this style. The only reason why I don't like using these is because it's missing the weather station models. So I don't get as much information from this as I would from the old ones that kind of look like they're hand drawn. So let's go further. Yeah. There we go. Okay, so up here, go. So there you can see the time and the date that this was recorded. And here you can see all the little station models that tell you about the weather at that location. I know it's rotated, that's why we're not going to use this one. Okay. So, just the basics. Synoptic weather map, that is the whole map that we were looking at. It shows you the general weather conditions over that area. And then a weather station model is a little collection of symbols. I know that's exactly what the definition says. Can't think of another way to paraphrase it. A little group of symbols that tells you about the weather conditions at that specific location at that time. And like I mentioned earlier, we always take it at the same time every day. So it's at 2 o'clock. That's when the data gets gathered and put onto the map. Okay, this is the weather station model. In school, you generally don't need to know all of this. I'm just going to highlight the most important things. So the first one is the round circle. The round circle shows you how much cloud cover there was at that time. This is measured in fractions, and it's not perfect. You estimate it. You kind of gauge it. So it's measured in fractions and it's measured in eighths. And I'm probably pronouncing it wrong, but it's octaves. 8 octaves. Okay, we have pressure over here in millibars, but I'm not really going to use these because I always encourage my students to use the isobars instead. So I'm going to put a pin in that. We're not going to really cover this representation of pressure. Then we have temperature in Celsius. That is always the one that goes at the top. So this is the current temperature when this was recorded. Then you have dew point at the bottom. Now, I don't think we've really gone into this yet, but dew point tells us how cold or what temperature the air needs to be for the water to condense. So there's always humidity, or I say always, there's pretty much always humidity in the atmosphere. And that that humidity influences how cold it needs to get to condense. So you can think of it as a sponge, water. And you've got a sponge and it's full of water, and if you squeeze it a little bit, all the water will come out. But if the sponge is basically dry, you have to squeeze it a lot before the water will come out. And the air acts the same way. The air is holding water in it, just like a sponge, and when it gets cold, it contracts and it squeezes. So it, depending on how much water the air is holding, will tell you how much it needs to squeeze before it will actually release and condense the water. So that's the mini explanation of dew point. So this is how cold it needs to get before you'll have any precipitation. Bearing in mind, this won't necessarily be the temperature at the ground. So this might be the temperature we experience, that 12 degrees. But it doesn't have to be 5 degrees by us for there to be rain. And the reason for this is because the rain, the condensation, doesn't happen on the ground. It happens higher up in the atmosphere. So naturally, it is colder higher in the atmosphere. So for us, we might experience the temperature as, let's say, 10 degrees. But as you go up in the atmosphere, colder and colder and colder, and somewhere in the higher levels, it might be 5 degrees and cold enough for condensation or rain. Okay, then over here we have current weather. All of these different symbols I have put together so we can take a look at them. Each of these symbols means something. And I don't usually use these weather since last measurements, but it'll be the same set of symbols. So temperature at the top, dew point temperature at the bottom, and current weather in between. Okay, then this tail with these little feathers, that tells you the wind speed and the wind direction. The wind direction, we use your north, east, south, and west. So this is pointing between north and east. So it's a northeasterly wind. Fairly simple. If it's pointing that way, it would be a westerly wind. Okay. Then over here are these little, I don't know how to refer to them. I always just refer to them as feathers. I'm not quite sure why. It kind of reminds me of an arrow with little feathers at the end. Okay, so these little lines tell us how strong the wind is, or the wind speed. And this is always measured in knots on these. I think that covers everything so far. Does the general collection of symbol make sense before I go into each one? Yeah. So let's start with the clouds, octaves. If you have an open or a circle that is empty, that is clear, no clouds. Okay? If you have a line going through it, that's one octave. If you have a quarter cut out, this is where I was saying it's basically fractions. It's a quarter is 2/8, so 2 octaves. Then where's the 3? I just realized this is in tenths. That's not right. I've got the wrong. Oh, No, no, let me fix these. Ah, that's not right. Why is it giving it a... No, no. No, don't do that. Being difficult today. Hello, welcome back. Oh, no cloud. There we go. We can always manipulate the diagram if we have to. Okay, then one line going through is 1 octave. I'm going to say that's like 1/8. Then this little quarter over here is 2 octaves. So 2/8. Hey, why didn't it automatically turn into a fraction like the previous one did? Oh well. Okay. Then where you have a quarter and a little bit of a line is 3/8. Now it worked. Did I do something wrong with this one? Okay. Here you can see it's half covered. So half of that is then 4/8. Basically a maths lesson now. Great. So now we're over here. We have the half and another little line. So a half and one little line is 5 octaves. Here you can see we have 3/4. That is 6/8. Okay, because we can't keep adding in another one little line, instead we're going to say it's basically completely covered, but it's missing a little piece, so that is 7/8. 7 octaves. And then the last one, completely covered, is 8 octaves. Okay, then this one with a cross through it means that the sky was obscured. So we couldn't take a reading at that time. It's not the fact that there's complete cloud cover so we couldn't see the sky. It's that we couldn't record the cloud cover. There. Now that looks right. So if we go back to this one, here we can see that it's basically completely covered, but there's one little piece missing. So that would be 7 octaves or 7 octaves. Okay. The next one is wind, and we record wind speed in knots. My students often ask me, like, how do we convert it to kilometers an hour or meters per second or whatever else? You don't need to. You just need to be able to read it from this. Okay, so I have it broken down for each symbol, but I'm going to show you that it's a lot easier to learn these 3 symbols than every single one of these. And you're going to realize that it's just a matter of counting. So where you have this line and a little half a feather, half a line, that represents 5 knots. And you'll notice that it's sometimes difficult to tell, is that a half a line or is it a full line? If there's only one line and you don't have another line you can compare it to figure out is it small line or is it a big line, you'll notice that it's not on the very end. See over there. So if it's not on the very end, then it's a half a line. And a half a line is 5 knots. Okay. If it is all the way at the end, then it is a full line and it's 10 knots. And now it's just a matter of counting. So that one is 5, half a line. That one is 10, full line at the end. That is 15, 10 plus 5. This one is 20, 10 plus 10. This one's 25, 10 plus 10 plus 5. Are we seeing it's very straightforward? And we can keep going up. So here we've got 1, 2, 3, 4 long lines. So that means 40 knots. 1, 2, 3, 4 long lines and a half line. So that's 45 knots. But usually around here it starts to get cluttered. So we've added in a new symbol. And that is this triangle. The triangle is 50 knots. And now we continue. There we go. 50 knots, triangle. Triangle and a little half line, 55. Triangle and 2 long lines, 70. Okay, we're seeing it's very straightforward. Once you have memorized these 3 symbols, you can read them very easily. And then we have weather. These are some of the symbols that I have made note of. So a little comma is drizzle, triangle is shower, dot is rain. I always like to test the thunderstorm one because I think it looks really cool. It's like a R with a zigzag. We have snow showers, so when you start to combine the symbols together, so that one is snow, and then the triangle shower, so it's snow shower. 2 lines is mist, and 3 lines is fog. If you're not sure, the main difference between mist and fog is just visibility. So if you can see further, then it's mist. If you can't really see, then it's fog. Now we're going to go back to what earlier diagram. There we go. So we have a long line and we have a short line. Do we know what this wind speed is? Okay, long line is 10, short line is 5, so together 15. Then current weather, we've got 2 little symbols that we've put together. The dot is rain, triangle is showers, so it's rain showers. Suddenly this is looking a lot easier to read. So we've got almost complete cloud cover. We have 15 knots of wind coming from the northeasterly direction, and rain showers, and it's 12 degrees Celsius. That sounds like hot chocolate weather. Is this seeming okay so far? Okay. No objections, so I'm assuming it's fine. Usually when I ask if the stuff makes sense, I can see from the students' faces. They're either like, yeah, yeah, or they're like, I've got no idea. They won't say that they don't know, they'll just stare at you. At a certain point, you can read your students' answers even without them. Okay, no, we're not going to jump to that. I first want us to look at some. Oh, why did it do that? Sorry, I don't know if that was just on my side. I think. Okay, I do actually have a problem. I don't know. Oh, there it is. I found it. I feel clever now. On the Zoom button. Jamie. Okay, let's pick one. Okay, we have Pretoria over here. I'm choosing Pretoria because I can kind of make this all out. Can you see it? Let me try and zoom in a little bit more. There we go. There's Pretoria. There's our weather station model. If there are any geography students watching this, usually maybe just double check with your teacher, but as far as I know, at least in my case, you are allowed to take a magnifying glass into the exam venue with you. Maybe just double check with your teacher about that. But magnifying glass for map work is fantastic. I'm sure you've seen those topographical maps. The symbols are so tiny, and you're trying to make out what that number says. There's nothing wrong with having a magnifying glass in the exam venue. That's if you're allowed to. Okay, so we have Pretoria. Let's start with the temperature. So temperature, 24 degrees Celsius. Remember, always Celsius. 24 degrees Celsius. And this bottom one, that's not minimum temperature. I often hear that get answered. That's not minimum temperature. That is dew point temperature. So that's the temperature it needs to reach for there to be any precipitation. Okay, and that is 13 degrees Celsius. Let's do wind speed. No, let's do wind direction first, sorry. So that is north, east, south, west. This is then between south and west. So it's a southwesterly wind. Yay! Okay. And it's a little bit, see, this is exactly what I meant by it's difficult to see if that's a long line or a short line. But you can see it's not at the very end. Zoom in a little bit more. Completely pixel. But it's just to show you. There. So there you can see the line is not all the way on the end. That means that that's a 5. That's 5 knots. Okay, and then our cloud cover, we can see that is 3/4. So that is 6 octaves. So we've got a fair bit of cloud cover. We've got 24 degrees Celsius, very gentle wind of 5 knots, and not yet a dew point, so I would assume that there isn't any rain at that time. Okay. I don't see anything that could, oh, that could indicate some type of precipitation. What is this? Is that just completely blocked out? I'm not quite sure what that's supposed to be, if that's supposed to be a symbol or something, but the border is going straight through it. Okay, let's take a different one. Let's take this one over here in the middle of the ocean. A little bit more. There. So I'm taking this one because it doesn't have any line indicating wind direction or wind speed. I would from this assume that it means that there's calm conditions, that there is no wind being recorded. I'm hesitant to say that for sure because usually calm conditions is 2 circles. So one inner circle and then another circle around it. So it's possible that this one is calm conditions, or it's possible that they didn't record any wind at that station. Okay, the other thing that we can see is that there is no clouds. The little circle is completely clear. It's 21 degrees and 19 degrees is my dew point temperature. So that means that there's probably quite a bit of humidity in the air over there. Speaking of humidity, I want to point out this one. So, okay, that one's blocked out. So let's take this one. Here we can see that we have 38 degrees. That's the current temperature. And 2 degrees is my dew point. That tells me that the air has to cool a lot from where it is to where it needs to be for there to be condensation. What that means is the air is very dry. There is not much humidity. So again, you can think about that sponge. You really need to squeeze that sponge before any water comes out. That's because it's very dry. So over here, you're probably having very dry conditions. There, there, there. That makes sense. It's quite far inland. This is very dry areas. Over here, the fact that we have a 0 degrees, that means that if it does finally condense, if it does reach dew point, it won't condense to water. So actually, it won't even condense. It will just immediately freeze. So what you would have is deposition. So it would go from a gaseous state to a frozen solid state. That's referred to as deposition. Okay, I think we've done quite well with our weather station model so far. We can read all that we need to. Okay, so these are some of the points that we're going to be looking at when we look at the map. A very important line to know is the isobar. Isobar represents pressure. So you may have seen contour lines on a map. Let's find contour lines. I'll show you what I mean. Trying to find one that actually looks a bit like a map. That looks like a map. Yeah. So if this is the map, and here you have these lines all over them. The lines show you altitude, so how high that point is above sea level. And there's a lot that you can figure out from these lines. So the lines, yes, they show you altitude. They can also show you things like gradient. So depending on if the lines are close together, so let me open up this one. Yeah, if the lines are close together, it means it's very steep. If the lines are far apart, it's more gentle. If the lines, see what else, what do the lines do? Certain shapes in the lines can show specific landform features. Example, you can kind of see it over there. Certain, open, a little bit bigger. Oh, this looks like a nice site. Maybe check this out sometime. I don't see it very clearly on the picture, but over here we can see it's like a little V shape. These little V's that are pointing into the same direction. That shows me that there's a valley over there. And this little blue line, that's my river going down the valley. So you can interpret things about the landscape from these contour lines. If you want me to do a video on contour lines, again, let me know, send message on the chat, send message on the comment section, wherever you're watching this. Happy to do exam prep videos. Okay. So in the same way, come back. So in the same way, we have lines all over a synoptic weather map. These lines don't measure height, they measure pressure. And they also have intervals. They are recorded in hectopascals, HPA. They go up in a set interval. Usually that interval is 4, at least when we see it on these maps, they're usually 4, but not always. Just check. So we can use contour lines as an example of how you check for an interval. I think you guys can see the numbers. Now let's just bigger. There we go. Now you can see the numbers. Okay, so here you can see it's 1,100. Here it's 1,200. So the gap from there to there was 100. And it's the same thing. So this is looking at it as a map. There's your 1,100. There's your 1,200. So from there to there, the interval is 100. On our synoptic wave map, there's my numbers. Now go away. Here are my numbers. 1020, 1016, 1012, 1008. So the gap between each of these lines is 4. So 4 hectopascals is my interval. When I ask my students to give me the pressure at a specific point, so if I gave them, I'm going to go back to Pretoria, I gave them Pretoria on the map. Here we go. If I gave them Pretoria on the map, and I asked them to give me all kinds of weather conditions, including pressure. What they would then be expected to do is look at what isobars it is between. Zoom out a little bit more. Okay, so we have one line there and we have one line there. So Pretoria is between these two lines. Now we need to go find what is the value of these lines. Oh, wait, here's more lines with numbers. That's 12. 2012. This is 1016. Okay, that's kind of helping. Oh, there we go. There's our values. So this line, you can see it traces all the way down to 1016. This line, so on the other side of Pretoria, go all the way down, and it's 1012. No, Pretoria was there. Now we have the values for these lines, 1016, 1012. I would allow range for my answers. So it can be anything between 1016 and 1012. But it can't be exactly those values. So I won't accept 1016 or 1012 because if that is the pressure, the line would be going through Pretoria. So it has to be anything larger than 12 or smaller than 16. So I would accept 1013 to 1015 hectopascals. Okay, that is how we would measure pressure from a synoptic weather map. Wow, there's like so much that we can go into about these maps. I've got so much in the notes, and I realize it would take so long to go through all of it. It's fine. We see how far we actually get, and I'll happily do another video covering the rest. What we're doing so far is the basics. This is what you would be expected to know at grade 10. Next, we have looked at the isobars. We've looked at the basics of the isobars. Put this back. Isobars indicate pressure and are measured in hectopascals. And we've added over here that the intervals, that's the difference between the two lines, is usually 4 hectopascals. I have made the mistake on many occasions when I'm marking students' work and I have assumed that it's 4 and I didn't realize until afterwards. They're like, why did we get these answers wrong? Because actually the interval was 6 or 5 or whatever else. It's just because I didn't read the math properly. Fine. It happens to all of us. Okay. Then the next thing to look at are high and low pressure cells. Where you have isobars that complete a loop, so technically they will always connect around to a loop again, but where you can see they make this enclosed circle, that is a cell. The cell will either be high pressure or low pressure. And there are two different ways. Oh no, man. This one. So this is a nice example. There is a closed loop. You can see that it's just been cut off on the bottom over here, but this would also be a loop. It goes all the way around. It goes up over here, there, and comes back. Okay, so this closed loop is a cell, and the H in the middle over there tells me it's high pressure. The other way that I know that this is high is because of the numbers. So if I start over here, 1004, and I go towards the middle of the cell, I can see the values go up. So that's another way that I can tell that this is high pressure. It increases towards the middle. So there's two ways. One, you can tell with the H. Two, the values go up towards the middle. Then, the other one we have is a low pressure cell. I'm not going to use that one because it doesn't look like a nice cell. Find a different one. There we go. That one looks nice. Okay, we have the little loop around the L. The L means that this is low pressure, and the numbers decrease towards the L. As we go there, it gets lower and lower in value. So this is a low pressure. Are we happy with that? Good. I'm glad that we actually found this map because you can see that there's a slightly different line. I don't know if you noticed this one. This has a little dotted line. The dotted line means that the pressure has decreased. So it's like there's a little dip right here. So it's decreased, but it hasn't decreased a whole 4 hectopascals. So it doesn't necessarily get its own isobar, but it gets a dotted isobar because it's gone down by 2 hectopascals. So this is a coastal low. It's a low pressure system that's on the coastline. You'll learn more about that in grade 12. So this is a little coastal low, and it drops down to 1022, but it's not a whole 4 hectopascal interval. That's why it's just little dotted lines. Good. Oh, I see I have one more point over there about warm and cold fronts. So hopefully you would remember um, the warm and cold fronts that are related to mid-latitude cyclones. So I do have another video covering mid-latitude cyclones. So I'm not going to completely go into that now, but this is just to show you how to recognize a mid-latitude cyclone on a synoptic weather map. And I really hope that one of these maps has one. Okay, yes, that is a cold front, but I'm trying to find the whole system. Like this one. There's a few more cold fronts over there. Yeah. Ugh, again, another cold front. Okay, that's fine. We'll use this for the cold fronts. So you can see the little spiky ends. That means that it's a cold front. Spiky is cold. Little semicircles is warm. I'll still see if I can find an example. And because it's a cyclone, it moves clockwise in the southern hemisphere. So it will be moving that way towards the east, towards South Africa or Cape Town specifically. And usually that will then bring rain and cold conditions. Let's see if we can find an example. That. If we can find an example with a mid-latitude cyclone. June, July. I think July is most likely. Middle of winter. Okay, let's pick a random one. Yes, haha, we got lucky from the beginning. Okay, download that so I can rotate it. Yeah. Finding a quick downloads. Go. View it normally. Great. Okay, this is a mid-latitude cyclone. So it's a little bit difficult to see because of the fronts, but right over there, there's an L. That L tells me that this is a low pressure system and it is a cyclone. You can also notice how close these isobars are together. We probably won't have time to go into it right now, but the fact that they're close together tells me that this has a lot of strong wind. Where your isobars are further apart, the wind will be more gentle. I can kind of show you on the station models. So you can kind of see it. So most of these have two lines, so they're 20 knots. And then over here, where the lines are quite far apart, the isobars are quite far apart, you'll see that they only have half lines, so 5 knots. Oh look, another coastal low. Okay, what we have is we've got the cold front over there. You can see with the little triangles, the spikes. And oh, we actually have a chain of cold fronts. So there's a cold front, and there you I got so excited because I thought I found a nice mid-latitude cyclone, but one's actually a bit of a pain. There you can see it, the little semicircles. That is supposed to be the warm front. But right over here, we've got another cold front attached. So what that means is that further south, there's another mid-latitude cyclone. So we've got two mid-latitude cyclones connecting to each other. Let me see if I have another map that isn't being hijacked by a second storm. No, no. Um, hey, that one kind of works. Let's take that one. Map. There we go. It's small, but it will work. There's the L, the low pressure system. There's the cold front spiraling off there. And there's the warm front attached there. Now, if you remembered the section of mid-latitude cyclone, you would be able to tell me that right there, it's starting to occlude. So that is my occluded front. We've got cold and warm symbols next to each other. So that's where the air starts to overlap. Okay. Usually we'll only see these systems in winter, or our winter, the Southern Hemisphere. And it will bring rain for the Western Cape. That's our main source of rain over here. So when the cold front comes in, it brings rain with it, and we experience winter rain. The rest of South Africa experiences summer rain. And I think all of that gets covered in one of my earlier videos where I look at different types of rain. Okay. I think this might be the last little section that I'll go through, and then we can wrap up there, and I'll do a follow-up video some other time where we get into more detail. So keywords. Hectopascals, that is our unit of measure when we're looking at pressure. HPA, and that's how you spell it. And there's your HPA symbol. Isobars, we know now, is a line that indicates the pressure of that place, and the isobar intervals is the pressure change between those two lines. Then, these are two very important concepts. So this is what I was hinting at when I was pointing out how close the lines were and how it compared to the wind speed. Pressure gradient. Pressure gradient is the change in pressure between 2 points. And this you can think of as very similar to actual gradients. So in mountains or hills, when you're looking at contour lines on a map. And then you have pressure gradient force. Pressure gradient force is a force that comes from the pressure gradient. So let's first unpack what pressure gradient means, and then I can try and explain the pressure gradient force. I must say, before I go into this, I think this whole apple illustration is really cool. Anyway, it's all good and well for me to see the diagram, but I want to make sure that you can also see the values on the diagram. And I'm working quite a large screen, so it's easy for me to. This can work. Yeah, that's nice enough. So each one of these lines in this case is showing altitude. These are the contour lines. And if you looked at it, you would see that the height goes up, the altitude goes up as we increase towards the middle. On this side, the lines are very close together, and you can see that means it's steep. On this side, the lines are far apart, and that means that it's gentle. This is basically pressure gradient. No, this is gradient, but this translates to pressure gradient. If this was a high pressure cell in the middle, kind of like how this is a high point in the altitude, you can imagine it as a ball rolling down a hill. And in the instance of the atmosphere, that ball is the wind. If we put a ball up on the top of there and it rolled down this way, it will roll quite quickly. If we roll it down this way, it will roll a lot slower. With the wind, it's the same thing. Wind always originates from high pressure. That is what I call my first law of wind. Wind always moves from high to low, kind of like a ball rolling from the top of the hill. If it rolls down that way, so if the wind blows this way, where the lines are close together, it's steep, which means that the ball will roll quickly, just like the wind would blow quickly. If it rolls down this way, where the gradient is gentle, it will roll slowly. And in the same way, the wind would blow slowly. I hope that is making sense. So if I to show you here, here we have a high pressure, here we have a low. So the wind will blow from the high to the low, just like a ball rolling down a hill. It would roll from the high part of the hill to the low part of the hill. Over here, you can see the lines are quite far apart. So it's not that steep. And the ball will roll slowly. The wind blows slowly. You can see if we look at, not much to compare it to, but if we look at the station models, we have anything from 5 to 10 knots. So not strong wind. If we compare it to this one, best example, but we'll use it. There's the top of the hill. There it's rolling down to the bottom. So my high pressure, the ball is rolling down, the wind is blowing towards the low pressure. And the contour lines are the isobars are very close together. So it's a very steep gradient. We zoom in, you can see that the wind is a bit stronger. And I know that you might be looking at this and saying, but that doesn't look like it's blowing from the high. That doesn't look like it's following the laws at all. Remember, I said the first law of wind is that it blows from the high to the low, but this looks like it's blowing from the middle of the ocean. Okay, that is a different topic altogether. That is due to a lovely force called Coriolis force. And I will happily get into that in another video. Okay, I think we can pretty much leave that there. I want to see if there was anything else. No, so this is just a simplified version of the same thing. So we have the high pressure here, we have the low pressure here. It will blow from the high towards the low, just like a ball running from the top of the hill to the bottom of the hill. And where the lines, the isobars, are close together, it's steep. Where they're far apart, gentle. So here the wind will be strong. Here the wind will be slower. Okay. I think I have covered that to the best of my ability. Yes, the next point is on Coriolis force. And I think we can leave that for another day. Has all of this made sense? I hope so. It's basics about synoptic weather maps. Like I say, they can get a lot more technical. We can read a lot more into them. I was showing you how we can look at wind speed. I was showing you how we can even look at humidity. We can tell if a place is dry or humid. Um, we also can look at synoptic weather maps when we're looking at the cyclones and anticyclones, be it mid-latitude cyclones, tropical cyclones. We didn't get to tropical cyclones this time. We can maybe look at the next time. Um, so yes, this is just a intro video to synoptic weather maps, and I really hope that it's been helping. Any other questions or thoughts? Are we happy? Great. Well, thank you very much for coming. I hope you had a nice cup of coffee. I know mine was. And I hope that you learned something interesting, maybe had some questions answered that you may have had, didn't realize that you had. And I hope to see you again next week. Please remember, I am happy to help with any exam prep, and just let me know if there's something you want to cover. Maybe leave something in the comments, and I'll put together another video for exam revision. Okay, have a lovely week.